12 grams for 1 mole of carbon and for 1 gram of 1 mole of hydrogen. So this is 0.0284 grams of hydrogen, and this is 0.3387 of carbon. So I take my original weight of the compound, which was 0.519 grams, and I subtract from that the weight of the carbon, 0.339, and the weight of the oxygen, which is 0.0284. And I should get an amount of oxygen that's left. So does that come out to be about 0.152? Okay, what I'm going to do is I'm going to subtract that from the original sample weight. Because the sample is made out of what? Carbon, hydrogen, and oxygen. So if I subtract the carbon and the hydrogen, I should get the amount of oxygen. So this should be grams of oxygen that are left. And if I change that into moles, 1 mole of oxygen is 16 grams. I get I think this number of moles of oxygen. And now if I have moles of oxygen, moles of hydrogen, and moles of carbon, I can take the ratio of those by dividing everyone by the smallest. So it looks like the oxygen is small. Did you lose anything?
So that's what he's going over.
Okay.
Yes, so go and turn it.
Okay. When you divide this by 0.00948, I think you get a 3. And this one, you get a 3. So the empirical formula must be C3H3O. And then if you take the empirical formula weight, I think it's about 55. And the given molecular weight was 154. This is about a 3.9, 3.8, something like that. So about 4. No.
It should be like
2.9. So it's about a 3. So you get C9H9O3 as the final answer. Okay.
I didn't get the right answer. Can we get like points for effort?
Well, depending on what you did correctly.
Hey, I just want something for trying because my brain started hurting and everything after that. And I'm still wrong. I suck.
Other questions?
Oh,
Yeah.
Basically.
Basically, yeah. And we've got a bunch of them that were turned in that are going to be late. You can turn it in. I'll look at it if you want me to. Okay. Any other questions? Yes. I brought 2 of them. People often wonder where I get these tricks from, and one way is in the back of magazines. You can find ads for all sorts of stuff. Like you can buy 100 pictures of yourself for $1, and dining room table pads for $13.95, and so forth. And there was this one magic trick that I thought, well, that sounds like a pretty cool trick. I think I'll get it. Came in the mail a couple days later, but didn't have any instructions. So I thought, well, I'm a pretty smart guy. I should be able to figure this out. It seemed like it was a silver tube that had these little wooden knobs and a piece of string on there, and that piece of string seemed to be connected to these 2 knobs on the right. And then as I played with it more, I thought, well, That's odd because it seems like this one is really connected to this guy over here, which I thought would have been connected to this guy over here, but he's connected to this guy over here, and this one's connected to this one over here, and both of those are connected to the guy on the end. So the moral of the story is, if you buy magic tricks in the magazines, get the instructions with them or you're in trouble. I only applaud if you mean it. Only applaud. All right, 2 tricks because you told me I'm behind. So nice of you to volunteer. Run my finger down the side of the deck when you tell me to stop. That'll be your card. Right here. Don't let me see it, but show the class. I'll turn my back so I can't see the card. Don't forget it. You need to write it down. Got it? Place it back anywhere you like. Don't let me influence you in any way whatsoever. No, it's a good job. This is a mentalist trick. I'm going to have to read your mind in order to do this trick. Anything I find there will be held in the strictest of confidence between us. But think of the card. Now, as I get my impressions, if I say them out loud, don't correct me. Don't smile, don't nod. That always gives it away. But let me see. I think your card is a black card. And I think it's an even number. So here's what I'm going to do. Any magician in the world could make her card fly out of this deck, circle your heads, and land in his pocket. I'm going to go a step further. I'm going to make a card equal to exactly 1/2 the value of your card. Fly out of this deck, circle your heads, and land in my pocket. If you had the 10 of diamonds, I would get the 5 of diamonds. If you had the 4 of clubs, I would get the 2 of clubs. If you had the 2 of hearts, I could get the ace, because the ace would count as 1 in that case. Okay? Now, the card travels very quickly. You'll have to watch closely or you'll miss it. Are you ready? Might do, man. Good try. Made it to my pocket. What was your card?
7 of spades.
Club.
7 of clubs? No, seriously. 7 of clubs?
7 of clubs. Yeah.
What's 1/2 of 7?
1/2 part of 7.
3.5 of clubs. Exactly the card that we were looking for. I know, I thought you had me.
Yes.
I did.
Sorry.
All right, we go on to chapter 4. Remember, even though the syllabus says that we're going to go to chapter 18 to look at redox reactions, because of the snow problems, we are taking that out of the picture. So there are no redox problems for you to work or to balance those reactions. There are some worksheets on the web. You can ignore them.
Yay.
That is not cause for cheer. Now in chapter 3 we took our first look at chemical reactions, and chapter 4 kind of refines these concepts a little bit. We did stoichiometry, which gives us a great deal of information about the chemical reaction, but we're going to expand that a little bit here. Chapter 4 talks about reactions that are in solutions, and 99% of what we do is solution chemistry. Chapter 12 actually defines solutions and gives you the properties of solutions, but that's for next semester. Those of you that go on to Chemistry 1212, we won't get to Chapter 12 in our course this semester, but it'll be revealed in its detail there. But we can't wait, and so we have to define some of the terms here so that we can use them, primarily because you're going to be using them in laboratory if you haven't used them in the laboratory already, and so we have to be familiar with them. Much of chemistry takes place in solutions. Over 90% of solution chemistry is aqueous solution, which means water. Water is a great solvent, particularly for what we call ionic or polar materials. And the descriptions of those substances will come later this semester. Let's consider table salt, ordinary table salt. It's composed of ions, sodium ion, and a chloride ion, and they arrange themselves in what's called a crystal lattice. The crystal lattice is sort of an ordered arrangement of those ionic particles in a solid structure. And we can actually see this on the slide that's going to be showing up here in a minute. But we can also see this extended macroscopically in real life. Your homework assignment today is to steal some salt. Go to the cafeteria, steal some salt, or go home and take some salt and dump it out of the salt shaker. What you'll find are little white particles, but they're not randomly shaped little white particles. If you look closely at those particles, you're going to find that they form perfect little cubes. Little cubes that have very smooth sides associated with them. Very sharp edges, very pointy corners. And the reason is because the ions that make up that large salt crystal, the sodium ions, which are the smaller, more white or yellow looking spheres here, and the chloride ions, which are the larger grayish looking spheres here, are in a very ordered arrangement with respect to each other in this crystal lattice, what we call a crystal lattice. So it forms a regular shape, and that's what you're seeing when you're looking at those tiny little cubes of salt when you tip it out and dump it out on the table. Now, other substances do the same thing, not necessarily in exactly the same format as this, but in what we call a crystal structure. And so crystals are common in nature, and you've probably encountered a few of them yourself with different substances. Now, when we put this salt into water, what does it do? If I dropped one of those little white cubes into a glass of water, what would we observe to be happening? It would dissolve. But salt actually does more than that in water. It not only dissolves, but when it dissolves, it dissociates. It breaks apart into the individual ions. Not all substances do this. Another thing that you know dissolves in water is sugar. If I took a little sugar crystal and dropped it into water, you would say the same thing. It dissolves. But when it dissolves, it simply dissolves. It does not break apart. The sugar molecules stay intact as molecules in a complete form and do not form an ionic compound. But the salt does interact with the water and does separate into these individual ions. Now, this is an old slide. It's a little bit hard to see, but you can actually see where the water is coming in here and causing these particles that were part of the crystal structure to leave the crystal structure. And they exist as single entities in the solution. There are little white lines here, whoosh lines, whoosh. There goes the chloride ion off into the solution. Whoosh. There goes the sodium ion off into the solution. And when it does this, it does it because the water interacts with those ions. Again, this is a topic of chapter 11 and 12 in Chemistry 1212 next semester. But we see it here taking place, that there's an interaction between what we call the solvent, the water in this case, and the solute, which is what we call the salt in this case. And the interaction is so strong that it causes the salt crystal to break apart. Notice that when it breaks apart, those waters are very fond of those ions. And they wrap themselves around them, not randomly, but notice that we've labeled the chloride as a negative ion. We're going to see why that's the case in the future. But the positive ends, or the hydrogen ends of the water, point in toward that negative ion. In the case of the sodium ion, the smaller particle here, look at the orientation of the water molecules. There are oxygen ends, which is the negative end of water, is pointing in towards that positive sodium. So you're getting a positive-negative interaction taking place there. And that positive-negative interaction is a strong one. And it's what causes the salt to be dissolved and dissociated into the water solution. And so those interactions take place and are very powerful. Now, as I said, when we talk about solutions, each solution has two components, or at least two components. One of those is called the solute, and one is called the solvent. The solvent is the easy guy. It's the guy that does the dissolving. 99% of the time, what is that?
Water.
It's water. So water is mostly always the solvent. The solute is the thing that gets dissolved. In the case of the example we just looked at, it's that sodium chloride crystal. That's the substance that's being dissolved. If you put a solid into a liquid, it's always the solid that's the solute, and the liquid the solvent. If you put two liquids together, then generally we take the one in the larger amount to be the solvent. So if I put a drop of alcohol into a beaker of water, I would call the water the solvent and the alcohol the solute. On the other hand, if I put a drop of water into pure alcohol, I would reverse those roles. I would say the alcohol is now the solvent and the water the solute. That doesn't happen very often. For most of the stuff we deal with, water will always be the solvent in our solution. The two together make the solution. And in the case of ionic materials like sodium chloride, these solutes will dissolve and dissociate into the solution. Again, not all substances dissociate. Sugar is a good example of something that dissolves but does not dissociate. Is there a test that I could run that would allow me to know that something has dissociated into its ions? The answer is yes. One of the things that we observe for a property for substances that dissociate in water is that they are electrical conductors. So I brought a little device today that we can take a look at. That indicates electrical conductivity. Here is a lamp. And this lamp has a cord that plugs in to an outlet, like so. And it has two electrical leads because one of the wires has been cut in half. And when cut in half, it means that the circuit is not complete. If I were to connect these two wires together, then the circuit should complete and the light bulb should light up. A couple of years ago, a student built me a safety switch so I wouldn't inadvertently electrocute myself in front of the class, although that would be a very effective demonstration. It wouldn't be good for me. If I turn the safety switch off, then contact of the two leads lead to electrical conductivity and the light bulb lights up. So consequently, anything I put between these two electrodes that conducts electricity should light the light bulb. So let's give it a try. I have some beakers here, and here is some distilled water. So I'm going to place some distilled water into the beaker. Now water turns out to be an extremely poor conductor of electricity. It kind of flies in the face of what you've always been taught. Okay, system works, let's try it. Put the electrodes into the water. Nothing, no lighting of the light bulb. And yet your parents have taught you never to stand in the bathtub with your electric razor and shave. Why not? We very rarely have pure water. Even if you were to bathe in distilled water, as soon as you step into the water, the salts from your body would wash off into the water, and those salts are ionic. They dissolve in the water and make the water solution an extremely good conductor of electricity. So if I have some substances here, like table salt, sodium chloride, and if I were to put, let's say, exactly a gram of sodium chloride into the water, then what I should find is that now that solution becomes an electrical conductor. So I have my two electrodes, I plunge it into the water, and what do I find? A lighting the light bulb. Now notice I put that salt in there, where did it fall?
To the bottom.
To the bottom. That's where it's dissolving and dissociating. That means up near the top, there aren't very many ions, and so you see there's a very poor lighting of the light bulb, maybe even no lighting of the light bulb at some point. But the further down I go, the brighter the bulb gets because there are a large concentration of ions there. If I were to stir this solution up and spread those ions throughout the sample, now even near the top, I have a pretty good amount of ions, so I get a pretty fair lighting of the light bulb. Turn off switch, save life. Now, I know what you're doing. You're sitting there thinking, well, I'll put anything in the water, it's going to conduct electricity. Okay, not true. I'm going to take some water, That water does not conduct electricity. Let's take some sugar. This is ordinary table sugar, sucrose. Yes, sir?
Temperature effect?
Probably to some extent, but not anything that we would notice in this room.
Not for sugar.
No, sugar is not going to dissociate. I think if you heated it up high enough, well, first of all, you would just evaporate the water, and then the sugar that was left behind, if heated, would probably decompose into carbon dioxide and water. I don't think you're going to get to see any conductivity with it. So I put exactly 1 gram of the sugar into the water. Device works. Let's give it a try, and nothing. Even if I stir this up, the sugar is dissolving, but dissolving into molecules, not ions. Therefore, no electrical conductivity taking place. Okay, we call substances that dissolve well in water and dissociate well in water, we call them electrolytes. If they do this really well, we call them strong electrolytes. If they do it, but they do it poorly, we call them weak electrolytes. I have a weak electrolyte with me. This is a container that contains ammonia dissolved in water. It makes ammonium hydroxide. Now, it's a concentrated solution of ammonia. It's about 16 or so moles per liter, 15 or 16 moles per liter. That's a lot. That's a lot of substance dissolved into the water. But ammonia is what we call a weak electrolyte. It ionizes, but only a little bit, not a great deal. Consequently, if I put my electrodes into the ammonia water, I should see a lighting of the light bulb, but notice how bright the light bulb is when there's direct contact between the electrodes. Now compare that to what we get when we put it into the ammonia. There's a lighting of the light bulb, but I don't think it's as bright as it was earlier. Indicating what? There are far fewer ions present here than we would have liked. Now, let me contrast that by taking a beaker of water You know, water does not conduct electricity, or it's an extremely poor conductor of electricity. And then I have something called sulfuric acid. Sulfuric acid is a strong acid. And when we say strong acid, what we imply is that it ionizes very, very well, almost entirely. So, would you expect this solution to conduct the electrical current? Yes. This is about 18 moles per liter. So in the same ballpark as the ammonia. But I'm not going to use the 18 molar sulfuric acid. What I'm going to do is to place just one drop of the sulfuric acid into a beaker of water. Now remember, this was the concentrated solution of ammonia. Very poor lighting of the light bulb. This is one drop of the sulfuric acid into water. Can you see? We get an extremely good lighting of the light bulb, which means what? In one drop of sulfuric acid, there are more ions than the concentrated sample of ammonia dissolved in water. Always like to give a quiz. Here's some water. Here's a substance called barium sulfate. Barium sulfate. We've got a gram barium sulfate. Give it a swirl. Mix it up. Now you have to vote. How many people say barium sulfate will light the light bulb, conduct the electricity? How many people say barium sulfate will not light the light bulb? How many people say I have no idea what you're talking about? Okay, well, let's see. Device works, and no. Now, those of you that said yes, why did you say yes? Barium sulfate's an ionic compound, BaSO4. Those of you that said no, why did you think no?
Lucky guess.
Lucky guess, very honest. Okay? Barium sulfate is an ionic compound, but it turns out to be extremely insoluble in water. And what's the case? It doesn't only have to be ionic, it has to be ionic that will dissolve and dissociate in the water. And if barium sulfate doesn't dissolve in the water, you get no dissociation, you get no ion charge, and therefore no electrical conductivity. Barium sulfate is used medicinally and in gastrointestinal x-rays. Some of you may have had this if you have some kind of problem with your gastrointestinal tract. What do? They give you a barium milkshake, a chalky type of thing that you drink, and then they take the pictures. And what does that do? Barium is a very heavy metal, very large atom. Consequently, the x-rays don't penetrate it very well. This barium sulfate outlines your intestines, and they can get a pretty good look at the picture through the x-ray. Well, why doesn't it kill you? Barium ions are extremely toxic to us. A good way to kill a person, don't do this because then I'll have to testify in court that I told you this in class. But barium chloride, a soluble barium salt, is a very good way to kill somebody. The barium ions will enter their system and is very toxic to us. But we feed people barium sulfate. And the reason is, or the answer is that it's extremely insoluble. It does not form the ions. And it's the ions that are toxic to us. And so by putting it into our systems, if it doesn't dissolve, it's just passed through the system and exits the body as waste material and is not a problem for us. Yeah?
How do you know if the ion is dissolved in water?
There are some rules that we can go by. In fact, let me see. I think there's a set of rules in this chapter in your book that talks about.
They have a table.
Yeah, table 4.1 is a guideline of ions that will dissolve in water, and it tells you what some of the insoluble ones are and what some of the exceptions are to the general rules. I don't think I necessarily want you to learn those rules, okay? At this stage of the game, you'll probably need some help and be told this is soluble, this is insoluble, this is going to work, this isn't going to work, and that sort of thing. In Chemistry 1211, you get a little better flavor for it because we can relate to it mathematically. There are some mathematical terms and some constant numbers that we can use to indicate something about the solubility of the substance in things like water.
I have a question about the light bulbs. When you can get them in different wattages, like what do they put? I mean, it's just how does that work with, even though you might be getting the same amount of electricity from your home? Like how does it just?
How does a different watt bulb work?
Yes.
I have no idea.
Okay.
It's a physics problem, but I imagine that it has to do with the element that's inside the little connector between the two electrodes as to what kind of power the thing would put out.
Oh.
And so you put out more power, you get a brighter light. It's going to consume more energy in the process, and so.
So that doesn't really have anything to do with the ions, like how you had different.
No.
Okay.
Because you don't have ions running through your wires at home. You have just electricity running through your wires.
Right.
And then in the light bulb. So it's as if these things were permanently attached together. But if you wanted to do this test, and I'm not suggesting you do because this is fairly dangerous to have these live wires out and open. And so unless you know what you're doing, don't do this at home. I am a professional, okay? And don't want anybody to get hurt. Yes, ma'am.
So, is the sugar not an ion?
It's not an ion. It
It's just
dissolves, but it dissolves into molecules.
so it's a molecular
It's a
bond.
molecular compound.
Okay, compound. What is it composed of?
Carbon, hydrogen, and oxygen.
Okay.
So, kind of like our extra credit question, we could have decomposed the sugar by combustion and analyzed what its makeup was if we wanted to.
Okay.
But we didn't. Okay, so strong electrolytes, a lot of ions, light the light bulb brightly. Weak electrolyte, small amount of ions, will light the light bulb weakly. Non-electrolyte, no ions, will not light the light bulb at all. So, back to our chemical reactions. One simple but necessary criteria for substances to react is that they have to have physical contact. If I want substance A to react with substance B, one minimum criteria, the only possible way they have a chance of reacting with each other is they have to come in contact with each other. If I put A in a jar on the shelf and B in another jar next to it on the shelf, are they going to react with each other? No, there's glass in between them, there's no contact. Now, contact alone does not guarantee chemical reaction. My hand and this tabletop, they're in contact with each other, but thank God there's no chemical reaction going on, or I could be in serious trouble at this point. Right now, you're in contact with lots of different substances. Doesn't necessarily mean that there's going to be a reaction. But if there is a reaction that takes place that you observe, it means that the substances had to have come in contact with each other. For this to happen, it's often a good idea to have them dissolved in a solvent, because solvent allows for good contact between the substances. Now, there are, I didn't bring it. There are examples of solids reacting with solids. They are very rare, but they do happen on occasion. But for the most part, if we want substances to react, we have to get them into some kind of fluid condition. Maybe gases. Gases tend to mix with each other very well and can react with one another. Or if they're in a dissolved state or a liquid state. It's more frequently that they're in a dissolved state, especially if we're dealing with ionic substances and trying to combine them together. One of the reactions that we observe is called a precipitation reaction. Precipitation reaction means that when you mix two solutions together, you see the formation of a solid material. So in other words, something forms that is insoluble in the water. If we mix two things together that are simply soluble with each other, then they're probably not going to have any noticeable reaction. Here, I have some test tubes. This test tube contains sodium chloride, and this bottle contains potassium nitrate. So let me diagram that reaction on the board. Sodium chloride, NaCl, plus potassium nitrate. This type of reaction is called a double replacement reaction. When you have two compounds reacting with each other, it's called double replacement. Double replacement reactions are easy to remember. They're the kinky reaction. What happens? They switch partners, okay? And so switch the partners in this chemical reaction. Now when you do this, you need to be extremely careful. Remember, theoretically, at this point, you know how to write correct chemical formulas. And we don't ever want to write incorrect chemical formulas. So what happens when sodium chloride reacts with potassium nitrate? If in fact they switch the partners, the sodium should pair up with the nitrate. How did I know that was the correct combination?
The charges.
By the charges, because when I write a chemical compound, what's always true? The first guy listed is positive. Second guy listed is negative. And logic tells us that the positive guy from here is going to combine with the negative guy from over here. So, sodium and nitrate. So now my job is to think. All right, if I'm going to form a chemical compound between sodium and nitrate, what would that formula be? Sodium is a +1 ion. Nitrate is a -1 ion. So it would be truly a 1-to-1 combination. So I'm going to get NaNO3. The second combination will be the potassium with the chloride. Same thought process. Potassium is a +1. Chloride a -1. Again, a 1-to-1. Lucky coincidence here. And so here's the balanced chemical reaction for this process. Let's take a look at this reaction in action. Here is a tube that contains sodium chloride dissolved in water. It looks like water. You know that's the case. The sodium chloride just sort of disappears. The potassium nitrate is the same way. It looks like a water type substance. It's actually got potassium nitrate dissolved in there. Let's mix the two together. Wow. No apparent reaction taking place. Why? All these things are soluble. So what have I done? I put two soluble things together. They made two soluble things. And you know the soluble things look like the water that they're dissolved in. So has something happened here? Well, I've mixed the ions together, but the ions are separated from each other because all of these guys, all four of these compounds are soluble in water and have dissociated into individual chemical ions present in the water. Well, can I get a chemical reaction to occur? Let me try another reaction. If I take sodium chloride and silver nitrate, same type of thought process. You should do the double replacement, pair up opposite partners. You're going to end up with sodium nitrate again. You know that's soluble. And this time you end up with silver chloride. The difference is that if you look on that table 4.1 on page, I think it's 144 of your textbook, you'll find out that silver chloride is not soluble in water. So if I take a tube of sodium chloride again, ordinary table salt, and a bottle of silver nitrate, again, both of these look the same. They look like water solutions, water solution. This dropper's a little discolored, but I'll drop a few drops. You can see that they just look like water in the solution. But if I mix these together, there is an obvious chemical reaction that takes place. In this case, when the two mix and silver chloride is formed, silver chloride says, oh, I can't stay in the water dissolved, so it precipitates out as a white solid. And you can actually see those white solid particles falling down to the bottom. By the time we pass this around and take a look at it, most of the sodium chloride will all be gathered at the bottom of the test tube because of gravity pulling the solid particles down. And so a reaction has taken place. As I've said, we call this double replacement. There's a couple of other names for it. Exchange reaction is sometimes used, or metathesis reaction. Metathesis is this double replacement exchange of ions, usually leading to some kind of precipitation. How do we know if it precipitates? I've got that table in my book, which would give me a clue. Aha, silver chloride is not soluble. And I could have guessed then that it would have formed a solid material. Since you're not memorizing these rules, you would either need the table in order to make that conclusion, or be given some information along with it. So let's try another one of these metathesis reactions. See how you do. If I have barium chloride plus potassium sulfate. Okay, go. Take 12 seconds, try to complete the reaction, and see if you can come to a conclusion.
What's the charge for sulfate?
I think it's -3.
-3. Okay.
I think.
-3, which will make that 2.
Hold on, let me see. -2. You're right.
Okay. That's -2. Okay. And barium is +2, and that's -2.
Yes.
So
So
they're-
they're just
So we don't have to do
1 to
anything
1.
extra.
Right. It's just
Okay.
1 to 1. I was confusing it with phosphate.
I don't know. How do you know? How do you know that? Oh yeah, I'm not looking in the book. So your insoluble product is barium sulfate. And
Okay, so let's look at this together then. Remember what happens here, you're switching to partners. So the barium should pair up with the
Sulfate
sulfate. Barium is a
+2,
+2, sulfate
-2,
-2, correct combination,
1 to 1.
1 to 1, or BaSO4. Remember the positive always comes first. So we have BaSO4. All right, second combination, potassium with
Chlorine
chlorine. Potassium is a
+1.
+1, chlorine.
-1.
Correct combination,
two.
1 to 1, KCl. Our first job is to write correct chemical formulas. Our second job then is to balance the reaction correctly. And you don't balance by writing incorrect formulas. And so we get correct formulas, and then we balance by putting a coefficient, a 2 out in front here, indicating that this is what's needed for a balanced chemical reaction. Now, this reaction right here is what we call the overall or the molecular equation. It's showing everything. We have another format that we sometimes use. That other format is called the ionic equation. In other words, sometimes we want to just see what parts are actually combining. To know that, you would have to know that the barium sulfate is the solid here. That's what's forming. And what we would do is take out all the ions that remain as ions. These are called spectators. They're really just along for the ride. So has the chloride really done anything here? No, it was a chloride ion in this solution, it's a chloride ion in this solution, and it can be extracted from the information. So the net ionic equation would be barium +2 plus a sulfate -2, giving us the barium sulfate solid. And we call that the net ionic equation. A complete ionic equation would include the potassium ions and the chloride ions, but we rarely use that. We either use the molecular equation or the net ionic equation as a result here. Now, charges are very important. In other words, a barium ion and a barium metal are very different chemical species. And you do not want to confuse those. So can you just write a reaction and drop the charges?
No.
You can, but then the red pen will fly. All right? So you don't want to do that. You want to make sure you're representing the correct chemical species, showing what's present in the chemical reaction. Now, there's also a matter for freshman students of breaking it down too much. When we break down this chemical reaction, notice we broke it down into barium ions and sulfate ions. The sulfate ion is a polyatomic ion. Could this be broken down further? Well, theoretically, we could break it down into sulfurs and oxygens, but we don't want to do that. For one thing, that's not how it would occur in the solution. And for a second thing is that usually breaking it down into ionic form is a simplifying process. It's giving us a better look at the information as to what's happening in the course of the chemical reaction. But if we break it down too much, we're making it more complicated for ourselves. Now, how do I know to stop at sulfate? It's one of my polyatomic ions. I made a flashcard. I memorized that value. I know what it is. So as soon as you recognize that polyatomic ion, leave it in that particular form. And it's probably better for you. Now, in terms of chemical reactions, we've already talked about some. Acid-base neutralization reactions. Remember that I told you an acid was a substance whose positive component was hydrogen. A base is a substance whose negative component is hydroxide. And when you put those two together, you end up switching the partners. It's a metathesis reaction. And one of the partner combinations will always be water. When the water is formed, The other substance that's formed is a salt. At a future time, next semester, we're going to ask you to memorize 6 of the strong acids to know which ones give us the very strong lighting of the light bulb type of interaction. But for right now, you'll probably be given that information. There are some other things that classify as chemical bases. Carbonates and bicarbonates usually do. So sodium bicarbonate is actually termed a chemical base. And as a chemical base, it will react with acids in a neutralization type reaction. In this particular case, the formation of the water is not really obvious. Let's react this with HCl. HCl, hydrochloric acid, is actually something your body secretes into your stomach as an aid for digestion. You eat some food, you swallow, that food gets into the stomach, and the hydrochloric acid there helps to start doing some random breakdown of the food particles that are there. Sometimes, if you eat too much or if you anticipate food too much, your body secretes too much acid. The stomach has a lining that makes it very impervious to the acid. But there's a flap on top of the stomach that helps to hold that acid contained in the stomach walls. But occasionally, the acid will back up through that flap on the top of the stomach and enter the esophagus, which is the food tube that runs from your mouth down to your stomach. That is not lined with special chemical makeup to be impervious to the acid. So the acid irritates that tissue. When it irritates that tissue, it feels like a burning sensation. And it happens right in here, so what do we call it?
Heartburn.
Heartburn, or acid indigestion. And one of the cures for acid indigestion is to neutralize some of that excess stomach acid. And things like Alka-Seltzer or sodium bicarbonate, Arm & Hammer baking soda from your kitchen, is a very effective neutralization substance for the stomach acid. And so the product here, switching the partners, we would get NaCl. Switching the other partners, we would get H2CO3. H2CO3 is a substance known to us as carbonic acid. Carbonic acid is somewhat unstable and actually undergoes a breakdown into water and carbon dioxide being a gas. There's the water that comes from our neutralization reaction. The carbon dioxide gas is often escapes from the stomach area and comes out as a burp. So even in something as disgusting as a belch, there can be strong chemistry taking place behind it in the body. Yes?
So that would form table salt inside of you.
Yes.
What is the little symbol behind the T?
The little symbol behind that is a G for gas.
For gas. Okay. Thank you.
Okay? Remember, we're going to skip the oxidation reduction and balancing redox reaction stuff. That ought to save us at least a day's time. So let me see if I can get to what we're going to next. Whoa.
Dr. Brian.
I don't know. We'll get to some other types of reactions at some